Hi and welcome to this section where we would like to look at further examples on complex integration. So we are going to look at further examples on complex integration. Okay, so we would like to look at the contour integral or the closed path integral of path C, which we are going to describe in a short while, of z squared over z plus 1 dz. Okay, for paths defined by C1, which is given by the modulus of z minus I equals to a half, C2, which is given by the modulus of z plus I equal to 1 half, and C3, which is given by the modulus of z equals to 2. Okay, so we are going to make use of, in solving integral of this form, we make use of Cauchy's integral formula. Remember that Cauchy's integral formula told us that if we have a function f of z which is analytic inside a closed path C, okay, a closed curve C, then f of z naught, okay, can be given as 1 over 2 pi I times the closed, the contour integral of f of z over z minus z naught dz. Okay, and where z naught is inside C. This is very, very important for us to note that z naught is inside C. Okay, so let us see if we can make use of that. But before we go any further, we have to sketch our curves here. Let's see, C1, definitely you can see that this is a circle of radius, which is a circle of radius 1/2, which is centered at I. Okay, so we see that it is centered at I, and it is a circle of radius 1/2. So this is if that is 1/2, so this is 1/2 I, and this is I, so this should be 3/2 I. Okay, so that is the circle we have. Right, so our idea, well, the idea here, the goal, okay, the idea is going to be for us to try to transform this into this form here. Okay, have a singular point z naught, okay, such as in the denominator we have this form z minus z naught, where z naught is inside C. Okay, in this case our C, which is C1, which is represented by a circle of radius 1/2 centered at I. Okay, so we go ahead and then we see, or we notice that the integral here over C of let's say z over z squared plus 1 dz can be written as the contour integral, this is C1 over C1 of z over z minus I into z plus I. Please note that z minus I multiplied by z plus I, that's the difference of two squares, is going to be z squared minus I squared, which is simply going to be z squared minus I squared is -1, so this is z squared plus 1. Perhaps one would say that how do you begin thinking in this line of direction? Well, like I said, this is motivated by the fact that we have a point I, okay, in here, and we are trying to look for a way of how we can transform this here, okay, to look like this here, where z0 is like a singular point here, okay. Z0 is the singular point for the whole of this expression here. The point Z0 should make this denominator here run to 0. Okay? So let's see then. So you realize that still we can say that now this integral over C1 of Z over Z minus I times z plus I dz is equal to the integral over C1 z all over z plus I divided by z minus I dz. I suppose you can see that now this looks very familiar with this one here, because we have z minus z0. In this case, our z minus z0, where our z0 is I, and they told us that that z0 has to lie inside C, and indeed I lies inside our closed path there, or our curve. Okay? So you can see again that we would have transformed this, where now we have this is our f of z, and then this is our denominator, which is z minus z0, and we already have an expression for that. We already know that the contour integral over c of f of z over z minus z0. Of course, f of z here has to satisfy the conditions that it is analytic inside C, and for sure this f of z here, okay, which is z over z plus I, indeed is analytic inside this curve here. It is, and even on and inside C, so it is analytic there and even inside C. There is no point, okay, inside or on C which will make this z over z plus I non-analytic. Okay? Alright, so next, please note, I just want us to note something here, that if we were computing just the integral over C1 of z over z plus I dz, please note that by the Cauchy theorem this would be 0, because Cauchy's theorem told us that if our function, this one here, f of z, is analytic inside everywhere, is analytic everywhere inside C and on C, then this value of this function here is simply going to be 0. That is what Cauchy's theorem would tell us. Okay, but here we have a slightly different form. We have the f of z, which is z plus that over z minus z0. So here, if I can use our green, so we have here, that is that. Oh no, sorry. We are saying that the expression for it, we are writing the general expression for it according to the Cauchy integral theorem. Okay, we had this equals to 2 pi I times f evaluated at z0. Okay, so if you can go back here, we are going to say that this over c1 of z over z minus I into z plus I dz, we have written it as the contour integral over c1 of z over z plus I all over z minus I dz, okay, which we now know it is going to be given by 2 pi I times f evaluated at z naught, and we know that our z naught is equal to I, so this is going to be 2 pi I, then f of z naught is the same as f of I, but remember that our f of z is this one here, okay, so it is going to be essentially z naught, which is I, over z naught, which is I plus I, okay. So what we have next is 2 pi I times I over 2I, and what does this become? This becomes the 2 and the 2 cancel, then 1I and 1I cancel, and this becomes I pi as our solution. Okay, great. Now let us look, what if we wanted to integrate, it over the next part, C2, and what was C2 given as? C2 was given as the absolute modulus of that plus that equals to 1/2. So we realize that this is a circle which is centered at negative I and radius 1/2. So where is our C2 here? C2, we are going to sketch our C2. C2 now is a circle also of radius 1/2, but which is centered at negative I. So this is negative 1/2 I, and this should be negative 3/2I. So this is our curve C2. So ideally you can see that we are going to modify the equation such that this point here minus I lies inside C, okay, that z naught, the z naught should be equal to minus I. Okay, so this of z over z squared plus 1 dz, which we have said it's going to be the closed, okay. Let us just write down the short note form, that is z over z, we say this is z minus I, z plus I dz. So we have this integral over C2. Okay, now the transformation here is going to be, now we shall just change it and write it the other way around. We shall say it is z over z minus I over z plus I can be written as minus I. Okay, in other words, our z naught, this is our z naught, negative I is our z naught, and indeed our negative I lies inside C2, okay, because it is a circle of radius 1/2 which is centered at negative I, which is our z naught. So yes, so we know by the Cauchy integral formula that this is going to be given as 2 pi I f of z naught. In this case our z naught is negative I, okay. This is going to be 2 pi I, then of course again here this is our f of z, okay. So what would f of z naught, which is f of negative I, be? It would simply be negative I, this is negative I, then negative I minus I, which would give us 2 pi I minus I over minus 2I. Okay, and so this should give us positive. This should also give us pi I pi. Okay, yes, so this should as well, okay, this and that cancel, and the negative and the negative. So okay, so this should give us also I pi. Okay, great. So lastly, we want to see what if we want to compute it. We want to compute over C3 or Z over Z plus Z squared plus 1, or Z squared plus 1 dz. So we say this is the closed path over C3 of Z over Z plus I Z minus I dz. So we have this C3. Okay, maybe we should have sketched this first. So C3 is just this one here, absolute value of Z equals to 2, which is just a circle centered at the origin with radius 2. So where? Here, circle centered at the origin with radius 2. Radius 2. Okay, so radius 2, that means if radius is 2, what this point is -3, so radius 2. Okay, so with radius 2, it implies that it actually covers all of these points inside within it. Not so? Centered at that, and the radius here is 2. Because this is 1.5, then the next point here is 2. So it, and then this is -1.5, and then of course here this should be -2. So these 2 points here lie within that whole path there. So that means that we are going to have 2 like points, which are like 2 singular points in there. So that means that we shall have to, transform our equation here in a form which encompasses both points here. Z, actually we'll just leave it like that, because we have that both this point here, Z0 equals to minus I, okay, because here we write it as, we can write it this as Z minus I, okay. So essentially our Z0 is minus I here, and in this case our Z0 is just I as it is. So both this and this, okay, which can make this function here to be the whole function as it is, Z over Z plus I into Z minus I, to be, non-analytic, lie inside C3, okay. So and for that matter, we can clearly see that if we take this to be our f of z, our f of z is okay, because it is analytic everywhere. If f of z equals to z, it is analytic everywhere inside that circle. There is no point where it is going to be, non-analytic. So what do we do? Okay, so we can write it in a form which is more useful. Perhaps one can now begin thinking of things like partial fractions. So we can say that you're going to write z over z plus I into z minus I. We shall say let, so this is a over z plus I plus b over z minus I. Then we have a into z minus I plus b into z plus I, everything z plus I, z minus I, and then for z equals to I, So on the left hand side we have this, it's going to be equivalent to, if this is equals to I, this is 0. So we have I plus I is 2I b, and then b is simply going to be 1/2. So then for z equals to minus I, so on the left hand side we have minus I, and then if we put in minus I, the b will cancel. This is minus I plus I, that is 0. So we have minus 2I a, and then a is 1/2. Therefore we say that z over z plus 1 into z, what's it? Z plus I into z minus I is a, this is negative, right? Negative, positive, it's positive, okay. It's going to be 1/2 z plus I, then plus 1/2 z minus I, okay. So that would imply that our integral here over c3 of z squared plus 1 dz, which we wrote as that, over c3 of z over z plus I into z minus I dz, okay, is this over c3 over 1/2 z plus I plus the contour integral over that z minus I dz. Okay, so what is the best way we can do this? Maybe now we can just pull out the what is it? We can just say 1/2 integral over c3 over 1 over z plus I dz plus the integral over c3 1/2 1 over z minus I dz. So okay, so I think we can just now put this in the form where this is our f of z, and then this is in the form z minus z naught, and then this is the form z minus z naught. In this case our z naught would be minus I, okay, while in this case our z naught would simply be I. So when you simplify above, you simply have 1/2 then 2 pi I f of z naught, okay, but our z naught is minus I, then plus 1/2 2 pi I f of z naught, which is f of I, but it doesn't matter because our f of z is just a constant function. This is 1 1, so we have 1/2 2 pi I times 1 plus 1/2 2 pi I times 1. So this and this cancel, so we have pi I, and this and this also cancel. We have pi I, and therefore we have 2I pi as our solution. Okay, so one interesting thing to note is that 2 pi I, okay, is the solution. It is like we have added the integral over the first, if we had these two singular points in there, I, and this one here minus I. So the solution we got here, remember, was I pi, and the solution we have here is I pi. Then we have seen that the solution, by integrating over this path C3, is I pi plus I pi, which is 2 pi I. Okay, so that is quite interesting to note, and a beautiful result. So I hope you have appreciated. I don't know, I may have bungled a thing or two here in trying to explain singularity and what, but I hope you get the idea here. You can try to do further research on your own as well, and hope this will help you as you read further. And yeah, so do we have time for one more? I don't know. Let me see. Do we have time for one more, or should I consider it in the next? Yeah, maybe let us finish with this other example here, because it's just intuitive. If you want the closed path integral over C, you have cos of z over z minus 1 dz. Okay, and the part C is given by modulus of z equals to 3. So that path there, that path is given by let's see, a circle which is centered at the origin with radius 3. Okay, so with radius 3, so in here you realize that our z0 is 1, not so? Our z0 is 1. This function here, cos of z, is analytic. It is a trigonometric function. It is analytic inside our C and even on the boundary. Okay, inside and on. So this is simply going to be 2 pi I f of z0, which is 1. Okay, so this is going to be 2 pi I cos of 1, because f, this is our f of z, and this is z minus, and that is our z0. Okay, so my 2 pi I times cos of 1. Then you can simplify that. What about if you wanted to compute this, okay, over cos z over z minus 4 dz? Then this would be 0 by Cauchy's theorem. Why would it be 0? It would be 0 because our point here, z0, z minus z0 here. Okay, first of all, okay, z, they said if we were to use Cauchy's integral formula, then z0 must lie inside C, but in this case our z0, which is 4, does not lie inside C. Besides, Cauchy's theorem told us that if our function here, okay, is analytic inside, so this function cosine of z over z minus 4 is surely analytic within this circle here and even on the boundary. It only fails to be analytic at this particular point z equals to 4, because there it will be, cosine of 0 divided by 0, which will not be analytic. So, but they told us that if a function is analytic inside and on a simple closed path, then the value of the integral over that path f of z is simply 0. So that is why this would simply be 0 because of Cauchy's theorem. Okay, yeah, so plenty of stuff, and I hope yeah, okay, we'll see you in the next video. Thank you.